Hello students, welcome to the course Verilog HDL. So in this video, we begin with the module 4. Okay, so what and all we have in module 4. So there are two units in module 4. One is behavioral modeling and another is tasks and functions. Okay, so what is meant by behavioral modeling? That is the topic we'll consider, unit we'll consider first, and then we'll consider the tasks and functions. Okay. So behavioral modeling. Okay, so as in previous two units, we have seen the different types of Verilog programs. So first we started off with gate level modeling, and then we take up the data flow level description. Okay, so that means in your logic design, okay, so first IO diagram is there, then truth table you are writing, okay, and then from the truth table you are writing the K-map and you get the Boolean, simplified Boolean expression, and from that you are writing the logic diagram. Okay, so this is the design part. Accordingly, so this logic diagram one-to-one correspondence is with the gate level description. Okay, so Verilog gate level description, just whatever gate is there, just you call that instance, it becomes your first type of Verilog description. So then in data flow, it is a data flow between the registers. So we stopped till Boolean expression, and there is a one-to-one correspondence with the data flow description. Okay, so data flow description in Verilog. Okay, so now we'll go one step further. So we have seen in the data flow description that some of the cases writing Boolean expression design itself very difficult. For example, 4-bit magnitude comparator we have seen. Okay, so in that case, and there are some many instances in real time where you could not write the Boolean expression. So in that you could not write the data flow description alone. Okay, so such cases, it may be based on the pattern of input output, or it may be based on the some algorithm or flow diagram. So you need to write the program. So for that, so your data flow description is not sufficient. Okay, so you need to go one step further. So that is what we call it as behavioral description. Okay, so this is the next description one step further. So normally the whatever program you have written so far, if you have the truth table of that, you can have one-to-one correspondence with this. Along with that, there are some real-time functions like a function of a kidney, function of a heart, or a traffic light controller. These you could not write a Boolean expression, right? So it is very difficult with the functionality, some algorithm, as we are writing some C program, Java, how it is algorithm based. Same way in Verilog, the necessity today is to write the program at the higher level. Okay, because of the sophisticated tools are available to make it data flow level or gate level description or switch level description. So we can write the program. So that is what our importance. Okay, so here some of the digital designs also will come, and there are some of the real-time designs will come. That's why the combination of data flow description and behavioral description, we call it as the RTL description. Okay, combination we are using. Some cases in the behavioral blocks, we may be using the operators of data flow description. Okay, for example, when you are writing if else statement, you'll be using some relational operators. Okay, so such things. So that is a combination we call RTL description. Okay, so hope it is clear. So what is behavioral modeling? So that we try to elaborate here. Okay, and what we are going to see here we'll look at. Okay, so these are the topics we have in behavioral modeling. Structured procedures. Okay, they are initial and always. Initial you have gone through already in some of the stimulus blocks and all. Along with that, now we'll learn another keyword. Okay, so these are the two blocks which will be present in all the behavioral modeling. Okay, and then we'll learn about blocking and non-blocking statements, then delay aspect of the behavioral modeling. So we have delay control and event control mechanisms. Then we'll start with conditional statements like if else, then if else, nested if else, all these things will come in this. Then we'll learn about multi-way branching, like case statement we will learn. And then loops. Okay, so what are the loops available in Verilog, we will learn at sequential and parallel block mechanism, and then generate statement. Okay, so these are the topics you have in syllabus, so that will go one by one. Okay, so these are the learning objectives of this module. okay, or unit behavioral modeling. Okay, first we'll explain the significance of structured procedures, always and initial in behavioral modeling. Okay, so these are the important construct here. So it's behavior you have to understand first. Then in that again we'll have blocking and non-blocking procedural assignments. So earlier we have studied about continuous assignment statement, right? So assign keyword. So now it is a procedural assignments. About that we'll learn. Then delay aspect of the program we'll learn. So first understand delay based timing control mechanism in behavioral modeling. So there are regular delays, intra assignment delays, and zero delays. Okay, second part we will see event based timing control mechanism in behavioral modeling. So regular event control, named event control, or event or control. Okay, and finally level sensitive timing control mechanism in behavioral modeling. Okay, so delay aspect of the execution of statement we'll learn it here. Okay, next we'll learn about conditional statements. So this is where it is analogous to C programming language. So the way we will write little bit changes maybe, but it is the same way it is working as in C program. Okay, so if else construct we will learn. Then multi-way branching, like using case statements, and there are two variations are there in Verilog. They are case X and case Z statements. This also we'll learn with examples. Then there are four loops are there in Verilog. So they are while, for, repeat, and forever. Some of the things you have heard about in the previous programs. Okay, forever we have used in generating clocks. Okay, so we'll go through that. Okay, then sequential and parallel blocks mechanism in this behavioral modeling we will take up. Then understanding what is meant by naming of blocks and disabling the name blocks. Okay, so some of the blocks you can name it. Okay, so user defined names you can give, how to give that and how to disable that we'll see. And then finally we'll see some real-time examples how to behavioral modeling we do in for practical examples. Okay, so that is digital part. So these are the things we are going to the in this unit. So today I will focus on the first topic, that is structured procedures, initial and always. Okay, so this aspect we'll consider today. So before that we'll introduce behavioral modeling. Okay, with the increasing complexity of digital design. Okay, as I told you, okay, because of the complexity in writing gate level we go on for data flow description. Again in writing data flow description, expression writing is difficult, so we called it as complexity. That's why we are moving, right? Complexity of digital design, it has become vitally important to make wise design decisions early in a project. Okay, before beginning of the project itself you should have a proper decision. Okay, which one you have to go for. Designers need to be able to evaluate the trade-offs of various architectures and algorithms. Okay, architectures with respect to various hardwares, algorithms with respect to evolution in software, before they decide on the optimum architecture and algorithm to implement in hardware. Thus, architecture evaluation takes place at an algorithmic level. Architectural evaluation takes place at an algorithmic level where the designers do not necessarily think in terms of logic gates or data flow. That means gate level description or data flow description, but in terms of the algorithm they wish to implement in hardware. Okay, so everything is algorithm based. Okay, so they are more concerned about the behavior of the algorithm and its performance. Okay, so that's why behavior of the algorithm and its performance. Only after the high level architecture and algorithm are finalized do designers start focusing on building the digital circuit to implement the algorithm. Okay, so this is the hierarchy step how it is going to happen. Okay, various providers, Verilog provides designers the ability to describe design functionality in an algorithmic manner. Okay, so first part it was the necessity at the algorithmic. So now Verilog supports that also, that is we are relating. In other words, the designer describes the behavior of the circuit. So thus behavioral modeling represents the circuit at a very high level of abstraction. Design at this level resembles C programming, okay, more than it resembles digital circuit design. So now at this level, program looks like C programming, okay, more than digital circuit program. Verilog constructs are similar to C language constructs in many ways, like case statement, loop statement, if else, all this. Okay, only writing may be little changes. Verilog is rich in behavioral constructs, okay, that provide the designer with a great amount of flexibility. Okay, so these are some of the advantages of Verilog with respect to algorithmic decision or behavioral modeling aspect. Okay, fine. So with this, we will take up the first topic, structured procedures now. There are two structured procedure statements in Verilog. Okay, so one is always and another is the initial. The name itself says, okay, so just you have to use initial means what? Initialization. Okay, so it will be used only once in the program. Okay, so normally it is used in stimulus block most of the time, or in counter case. If you have to initialize the counter value to start from 0 or something, we will use this keyword. Then always is the main construct in behavioral modeling we'll look at. Okay, so what it has in it, these statements are the two most basic statements in behavioral modeling. All other behavioral statements can appear only inside these structured procedure statements. Okay, Verilog is a concurrent programming language unlike the C programming language, which is sequential in nature. So this is only the change with respect to C programming. C programming is sequential, one by one, whereas Verilog is concurrent. Okay, so simultaneously it will execute if there are separate blocks are written. Activity flows in Verilog run in parallel rather than in sequence, that is the meaning, and each always and initial statement represent a separate activity flow in Verilog. Okay, you can write in single module multiple initial statement, multiple always statement. Okay, but it could not be nested. Each activity flow starts at simulation time 0 and the statement always and initial cannot be nested. So this is important. Okay, so inside the initial you could not write always, inside the always you could not write initial. Initial begin you have written and you have to do again, you have to write separately as always. Okay, so nesting is not allowed. Okay, fine. So with this introduction we will introduce the first initial statement. Okay, all statements inside an initial statement constitute an initial block, whatever we'll write inside initial, and initial block starts at time 0. Okay, execute exactly once during a simulation and then does not execute again. If you have seen previous examples, okay, so in the data flow or gate level description we have seen many stimulus blocks we have written, even in exercises also you have written there multiple initial blocks. Okay, so recall that if you have the notebook, just you can recall. Okay, and all they will work starts at the time 0 and they will exact only once during the execution. Okay, so this is the definition of initial. If there are multiple initial blocks, each block starts to execute concurrently at time 0. They will simultaneously execute. Okay, and based on the number of statements in the initial or number of delay in the initial blocks inside that, so they may end at different time. Okay, but all will start at the same time. Okay, each block finishes execution independently of other blocks. This is what. Okay, so one initial block may be very small, one initial block may be very big. Okay, so one initial block may be having no delay, another initial block may be having some delays with the delay we have specified. Okay, so in that case, so ending is not same, independent. Okay, whereas beginning is at the same time 0. Multiple behavioral statement must be grouped, typically using the keywords begin and end. So this is holds good in all the behavioral constructs now onwards. So initial, if you have a single statement, for example, previous one stimulus module monitor statement we have written, it was a single statement. That's why begin and end we have not written. But whereas in the case of when we are exercising inputs, we have given begin and end because multiple statements were there. Okay, so this holds good for all. Okay, always also it holds good. Next, if else, case, loops. Okay, every Verilog this one it will holds good. Okay, if there is only one behavioral statement, grouping is not necessary, it is optional. Even if you write begin and no problem, but even if you omit for one behavioral statement, so it is not a syntax error. Okay, so this is similar to the begin and blocks in Pascal programming language. So it was there before C, right? So it is the same. Begin and blocks came from Pascal, and in C program we are using flower brackets, right? Int main, after that you are writing a flower bracket and then you are writing initialization, and finally you will, before closing you will write flower bracket like this, right? So this is the style in C programming, flower bracket Same way in Verilog behavioral construct, begin and end we are using. Okay, hope it is clear. Okay, we'll see the example to understand this initial. We have done already many examples. Okay, but still, module stimulus. Okay, register xy abm, there are 5 variables I have declared here, all of register type. Okay, initial m equal to 1 bit 0. Okay, so what I am going to show with this example is, in each of the blocks there are delay blocks, there are no delay blocks. How statements will, which statement will execute first here, that we are trying to say. Okay, so in this first initial I have not written begin and end because it is a single statement, does not need to be grouped. Initial you can write it in single line also, initial m equal to 1 bit 0. Okay, just for a readability it is written like this. Second statement, I have multiple 2 statements, that's why begin and end is compulsory here, otherwise error. Okay, so number 5 a equal to 1 bit 1, number 25 b equal to 1 bit 0. On the second block I have used ab, first block m, next block x and y I have used. Okay, so just to show you, next again you have multiple statement, that's why begin and used. So number 10 x equal to 1 bit 0, number 25 y equal to 1 bit 1. Okay, so now to understand, so the concept of how concurrently these initial statements will work. So first all the blocks will start at 0, all the initial blocks start executing at 0, but each of the block may not, they will complete the task at independently, they does not depend, they will not at a time. Okay, for example first one, if you consider there is no delay here, so it may be after some fraction of second, so this will be executed. So this is the first statement, it will be executed. Next if you go this block, so there is a 5 units delay, so that means a equal to 1 bit 1 will be executed. Next 0 plus 5. Okay, then this statement will be executed at 30 time minutes because 0 plus 5 plus 25 30. Okay, so after that here we will come, so here I have a delay 10 1 bit 0. Okay, so that means 0 plus 10, so this will be executed next. Okay, although it is in different block, so this is how this will be, first m, then a, then x. After that, so this 10 plus 25 35 it is, right? So that's why it will not execute. 5 plus 25 35, this will come. So fourth statement this will be executed, and last statement this will be executed. See here, so this initial block completed first, this block completed second, and this block completed last, independent. Okay, but started at the same time, depending on the delay in the program or number of statements in the program, so they have executed independently. Okay, so this is the idea to show you here. Okay, so the same thing only I will elaborate now. So finally initial $20 finish, so again here single statement, that's why begin and end are not written. Okay, in the example the 3 initial statements start to execute in parallel at time 0. If a delay is seen before a statement, the statement is executed that much delay time minutes after the current simulation time, that is delay concept. Thus the execution sequence of the statement inside the initial block will be as follows. This is what I have told you, that is I have summarized here, time and which statement will execute. So 0 time m equal to the first block m, right, that is executed. Then at time 5 units, so a will be executed from second block. Then at time 10 minutes, third block x is executed, right? Then again it will come back to the second block, b will be executed 1 bit 0, and at 35 it will execute the third block y statement. Okay, and finally at time 50 it is 0 plus 50 only, so it will finish the simulation. Okay, so this is the concept to understand this example was taken. Okay, the initial blocks are typically used for initialization, monitoring, waveforms, and other processes that must be executed only once during the entire simulation run. So this is the use of the initial block where we have to use it. Okay, so this is about the initial statement. So similarly we'll look at always statement now. So before that there are some different variations are in this. So combined variable declaration and initialization, how we use this small concept here along with initial. The following subsections discuss on how to initialize values using alternate shorthand syntax. The use of such shorthand syntax has the same effect as an initial block combined with a variable declaration. Okay, so this is an example here. So clock variable is defined first, register clock, and then it is set to 0. Okay, initial clock equal to 0. So instead of this above method, clock variable can be initialized at the time of declaration. This is allowed only for variables declared at module level. So where we have declared register clock, there only you can make it equal to 0, as in C programming. Okay, so no need to write separate initial also. This is combined variable declaration and initialization example. So a combined port or data declaration and initialization, same way. The combined port or data declaration can also be combined with an initialization. For example, module adder I have written sum C naught ABI and register sum equal to 0, C naught equal to 0 we have made. Initialize 8-bit output sum, initialize 1-bit output C naught. So this is how we write. So this we can do it in the port declaration itself. Okay, so that is the example. Next it is shown. So this is the initialization. So then ANSI style. Previously also you have seen this ANSI style port declaration can also be combined with an initialization. The same thing whatever run previously, now it is written inside this sum equal to 0, output C naught equal to 0. So this is allowed in ANSI style, right? Hope it is clear. So the initialization part. So next we'll consider always statement. So this is another big keyword used in behavioral. Okay. So in each of the description you will have the keyword. So in the case of this one gate level description, you have the primitive gates. If any of the primitive gates keywords comes, it is a gate level description. Okay. So in the case of data flow description, assign keyword is a main thing. In the case of now behavioral modeling, always or initial, anyone will be there. It is called as behavioral statement. Both can be present. All behavioral statement inside an always statement constitute an always block. Always statement starts at time 0 and executes the statements in the always block continuously in a looping fashion. So this is the difference to initial. Initial will start execute only once, whereas always, the name itself, always. So it will continuously run in a looping fashion unless you give dollar finish or you stop the or switch off the device, only then it will stop. Okay. This statement is used to model a block of activity that is repeated continuously in a digital circuit. Okay. In the real time, all the digital circuits, they will be repeated continuously, right? There is no need to off. For example, if you go to Bangalore or some metro cities, the traffic light will be on 24/7, right? 365 days. Only if some mistake is there, they have to correct it immediately, right? So it is working 24/7. So then you have to require always block, right? It is not a one-time show. An example is a clock generator module that toggles the clock signal every half cycle. So that is also an example real time. So that is clock. Clock is generated continuously unless you stop it. In real circuits, the clock generator is active from time 0 as long as the circuit is powered on. Okay. So inside what you have, clock generator only. So clock generator is an example here for always statement. So we'll see an example here. So module, okay, clock generator output register block, initial clock equal to 1 bit 0. Initially we have made the clock equal to 0. So then you have, it will toggle for every half cycle, that is time period is 20 year, delay 10, always 10, clock equal to not off clock. Previously we have used a forever keyword also, that also you can use. Even if you this also use continuously. Okay, initially it was 0, after 10 it will become high, and after 10 it will toggle again 1 to 0. Like this it will repeat continuously, it is on. Okay, and this time period is 20, 10 plus 10, on and off time, called as 1 PD. And $100 we have given finish, right? So only at that time it will finish. So executing that much time, after that it will finish, otherwise it will continuously on. So this is the idea of always. In example above, the always statement starts at time 0 and executes the statement clock equal to not off clock every 10 time minutes. Notice that the initialization of clock has to be done inside a separate initial statement. Initialization you could not do, because initialization if you write always, what will happen? Every time it will be 0. It will not change the value at all. Okay, that's why initialization part you have to use initial. Only for clock we have to use the always block. If you put the initialization of clock inside the always block, clock will be initialized every time the always is entered. Also, the simulation must be halted inside an initial statement. That's why whichever we have to. So this is an example to show you where we have to use initial and where we have to use always. If there is no stop or finish statement to halt the simulation, the clock generator will run forever. Continuously, it will run. So if there is a traffic light situation, if you have to stop means what? Traffic police will be there. He has the button there, okay, to reset. If ambulance comes, he will go and reset that path, right? So that is how, okay. So that option will be there for that case, okay. C programmers might draw an analogy between the always block and an infinite loop. Okay, so in C programming, we'll have an infinite loop concept, like those who are doing embedded system programming and all. Okay, so infinite loop concept they will use. Okay, but hardware designers they don't tell that term infinite loop, but just they call that as always block. Okay, maybe the functionality is almost same, but hardware designers tend to view it as a continuously repeated activity in a digital circuit starting from power on. Okay, so the activity is stopped only by power off or by an interrupt. Okay, so either you have to off the, that means finish, or you have to interrupt it, stop. Okay, interrupt it and you can restart it. Okay, so like that. So this is about the always statement. Okay, so hope something is understood to you from this lecture. So since it is a first video on behavioral modeling, so as we are going completely a different aspect in Verilog description, so the things are new, so you have to go through again and again. Okay, so hope it is clear. So we'll continue the discussion to the next topic in next video. Okay, so we'll end the session here. Thank you.